Hello, my name is Matt Eichhorn. I'm a PhD student in the Center for Applied Math at Cornell, and today I'm excited to share with you some recent work with my collaborators, Sid Banerjee and David Kempe, on allocations in settings with priorities and quotas. To motivate our problem, let's think back to the response to the COVID-19 pandemic, where at various points, different constraints on the supply chain place limits on the number of available medical resources. We saw this first with ventilators and later on with vaccine doses and antiviral treatments. In light of these shortages, we were forced to grapple with who should be prioritized to receive this medical care. One idea was to prioritize people based on occupation, first giving units to healthcare and other essential workers. Another thought would be to prioritize individuals with comorbidities who may be more likely to contract severe cases of the disease. And another thought would be to prioritize people based on where they live, giving the first units to residents of high density housing, where spreading of the disease may be more common. In light of all these different ideas, one can ask, what would be a fair way to allocate care? And some common answers for this would be either to choose one of these criteria and base our decisions solely on that, or to somehow create a scoring function that aggregates all of them down to a single number and use this to rank the individuals. However, these one-dimensional schemes have issues in that they could either ignore or systematically work against some of the very groups that we're trying to prioritize. Before I discuss our approach, I want to formalize the problem that we're looking at. In our problem, we have a set of agents A who each want to receive the unit. They have unit demand, and they're indifferent about how it is that they receive their allocation. And the way that we allocate is through categories. You can think about each category as representing one of these allocation ideals. So maybe the individuals with comorbidities would be prioritized in one category, whereas occupation would be the controlling factor in another category. And each category will have a quota, a number of units that it's allowed to pass out. It'll specify which agents it deems eligible to receive its units. And then among these eligible agents, it'll define a total pre-order to rank the agents based on their priority for receiving an allocation in that category. We can picture the allocation instance on the right with one of these T-charts, where each column represents a category, its quota is listed at the top, and the agents are listed from top down in the column, where the higher agents have priority over the lower agents. And in this problem, our goal will be to select an allocation map, which sends each agent either to a category where they receive their allocation, or to the outside option if they're unallocated, which we represent with this perp symbol. And what properties should we look for in this allocation map? Two natural properties come from our formalization in the previous slide. Each category should be respectful of its quota. It shouldn't hand out more units than it has. And the category should also respect the eligibility. They should never have to give one of their units to an agent that they deem ineligible. A third requirement is to respect priorities, and this one is a little bit more subtle. We say that an allocation is priority respecting if categories only allocate to agents once all of the higher priority agents in that category have been allocated, either through that category or through another category. We can visualize an allocation map by drawing circles around the agents if they're allocated in that category. We see that this allocation here respects eligibility, since only the eligible agents are pictured in the chart. It respects quotas, because no category is allocating more units than it has, but it's harder to see priorities. To do this, we'll add squares to the chart, which represent that an agent was allocated, but in a different category. So here I've drawn a square around B in category alpha, because B received an allocation through category gamma. Then the allocation is priority respecting, because we never have a circled agent sitting strictly below an unmarked agent. So far, these properties place constraints on the set of allowable allocations, but they don't yet give us any idea of whether the allocations are any good or not. For example, giving out none of the resources satisfies all three of these properties. So we need a fourth desideratum that can help us to encode a quality allocation. And for this, we'll use the familiar notion of Pareto efficiency. Here we'll say that an allocation is Pareto efficient if there's no alternate allocation satisfying our three properties that's able to give out resources to a strict superset of the agents. And then our goal in our work is to locate allocations with these four properties. So eligibility, quota, and priority respect, as well as Pareto efficiency. And we'll call these valid allocations. So in the rest of the talk, I'm first going to outline an algorithm to efficiently compute valid allocations that's based on an LP characterization of our problem. Once we have this characterization, it'll allow us to consider many different variants or extensions on the problem, and we'll think about complexity questions that we can ask about these variants. And lastly, I'll extend the problem to an online setting. Our algorithm is based on an integer programming formulation of our problem. Here we'll have a decision variable for each agent category pair that indicates whether that agent was allocated through that category. Then our objective will be to maximize the total number of allocations that are made. This will ensure Pareto efficiency, and we'll have constraints that enforce the respect for the quotas, the unit demand of the agents, and the eligibility requirements. Notice that this program that we've just written encodes a bipartite B matching problem, which notably means that it's totally unimodular, and it has all integer corner points. So we can safely go to the LP relaxation of this problem and know that our solutions will still correspond to integer allocations. The one thing that's missing from this program is any sort of way to encode respect for priorities. Here we show an example of an allocation that corresponds to a solution to the program on the previous slide. Notice that in this allocation, every category exhausts all of its quota, so we are Pareto efficient. And we respect eligibility and quotas automatically. However, this allocation does not respect priorities. Notice that in category alpha, we've allocated to agent D, while the higher priority agent C was not allocated anywhere. Let's try to get some geometric intuition for what's going on here. When we solve our linear program, it'll pull out one of the corner points of the optimal face of our constraint polytope, which we know corresponds to integer allocations. And some of these allocations will be good. They'll respect priorities. These are depicted in the picture by the black points, while others won't respect priorities, like the allocation that we saw on the previous slide. And we need a way to be able to select out only the good allocations. And the way that we'll do this is by slightly tilting the objective direction, which will have the effect of removing some of these corner points from the optimal face. And we'd like to do this in a way which only leaves good corner points. And we can think about this tilting of the objective as doing a small perturbation on the coefficients in the objective, which we do with these parameters delta AC. Now, what properties do we want from these deltas? Well, we want to choose a perturbation that actually enforces respect for priorities. And we could do this by more heavily penalizing allocations to lower priority agents in the category. And the second thing that we want is that we never want these perturbations to actually reduce the total number of allocations that are made. And we can do this by ensuring that the sum of all of the perturbations is sufficiently small. We call a perturbation delta valid if it satisfies these two properties. This brings us to our first main theorem, which says that any solution of the program P delta for any valid delta corresponds to a valid allocation. This gives us an efficient algorithm for finding valid allocations, since solving P delta is really just solving a weighted bipartite matching problem. One can ask whether there's a converse to this result. Namely, we know that choosing any of these valid perturbation directions will always allow us to identify a valid allocation. But the set of directions that we're allowed to tilt to is restricted by the property that the perturbation has to be valid. And so one can ask whether the allowable angles that we can tilt the objective allow us to locate any of the valid allocations. And we have a theorem that says, yes, for the most part, if you tell me any set of agents who receives a unit in a valid allocation, there's some valid perturbation we can pick that will locate such a valid allocation. I've just described how we can reduce the priority respecting allocation problem to a weighted bipartite matching problem. And moreover, the restrictions that we place on these weights for the perturbations delta are minimal. So one can ask, how can we extend these ideas in order to handle some related problems? And while we've considered a lot of different extensions, I'm going to highlight two specific case studies today that kind of demonstrate the computational knife's edge that these priority respecting allocation problems seem to lie on. So I'll present two different extensions, each with two slightly different variations. One of the variations will be easy. We can handle it with a small modification to our algorithm, while the closely related extension will be NP hard. In our first case study, we'll focus our attention on one particular agent A. And there's two natural questions we can ask about agent A. First, we can ask whether it's even possible to allocate to them. And we say that an agent is serviceable when there's some valid allocation that gives them a unit. And the related question we can ask is whether we need to allocate to agent A. And we'll say that A is unanimous if they're a recipient in every valid allocation. It turns out that deciding whether an agent A is serviceable is NP hard, which we show via a reduction from the X3C problem. On the other hand, we can decide whether an agent is unanimous by a small extension of our algorithm. In our paper, we show that every valid allocation allocates to the same number of agents. So to decide whether an agent is unanimous, we first compute this valid allocation size. And then we modify our instance by removing the agent A and all of the lower ranked agents. We call this taking a restriction of our instance to agent A. And we're left with fewer agents eligible in each category. Now, in this new instance, we again compute a valid allocation. And here we see that the total number of allocated agents went down from 4 to 3. And this certifies to us that the agent A is unanimous. They need to be included in the allocation in order for it to be valid. The second extension that we'll look at is to incorporate agent utilities. At the beginning of the talk, when we formalized the problem, we assumed that agents were indifferent about where they were allocated. However, this likely isn't true in a lot of allocation settings, such as the allocation of school seats or public housing. And in these settings, we may want to equip an agent A with a utility function, U of A, that allows them to express how much they like allocations from different categories. And armed with these utility functions, we can think about two possible extensions. First, we could try to find an allocation that's Pareto efficient with respect to these agent utilities, meaning there's no way for the allocated agents to organize a trade of the categories where they receive their allocations in a way that increases all of their utilities. And the second thing that we could ask for is to find an allocation that maximizes the total utility of the allocated agents. Here, calculating a utility Pareto efficient allocation can be done using two passes of our algorithm. In the first pass, we locate any valid allocation using an arbitrary valid perturbation delta. And from this allocation, we take the set of recipients. Now, we restrict the instance by removing any of the agents who were not allocated from the instance. And then we run a second time, but this time we choose the perturbation based on the agent's utilities. And this will ensure us Pareto efficiency. On the other hand, maximizing the utility of the allocated agents is NP-hard. And we can show this via a reduction from the serviceable problem from the previous case study. The idea of this proof is that one agent will have very high utility in all of the categories, while the other agents will have low utility. And so in order to maximize the utility, we need to be able to decide whether we can find an allocation that gives to that one particular agent. And we can take this proof and generalize it to consider different objectives to optimize for the utility, such as the Nash social welfare. In this final part of the talk, we'll consider an online variant of the priority respecting allocation problem, where over T rounds, one agent will arrive in each round, and we need to immediately and irrevocably decide either which category they'll receive their allocation, or we can choose to not allocate to them. In this online setting, it no longer makes sense to think about a fixed set of agents, or this would just revert us back to the offline problem. And instead, we'll think about a finite set of agent types. Each of the categories will specify eligibility and priority with respect to these types. And in each round, the type of the online arriving agent will be drawn from a known probability distribution P theta. In this online setting, we could try to choose an allocation that satisfies eligibility, quota, and priorities and allocates to a maximal extent. However, this won't work so well. And we can argue that if we insist on not having any priority violations, there are instances that require us to incur an omega t loss in the efficiency with high probability. We don't like this omega t. Ideally, we'd like the total loss that our algorithm experiences to be constant with respect to the size of the instance. Rather than enforcing respect for priorities as a hard constraint, we can treat it as a secondary objective in our optimization problem, trying to minimize the number of priority violations in the allocation that we calculate. And in our work, we describe an online algorithm that ensures that in expectation, the total efficiency loss plus the total number of priority violations is bounded by this expression here. Notice that this is a constant with respect to the instance size, so with respect to the number of arrivals and the total quota. But it does depend on some other parameters of the instance, namely the number of types, the number of categories, and the minimum probability of a type arriving. And fundamentally, this algorithm relies on our LP characterization of the problem. To wrap things up, in economics and CS, we typically think about fairness as a single objective function that we wish to optimize. However, this may not be the best approach in many cases, like the COVID example that we looked at earlier. Rather, we feel that categories provide an instrument that can allow us to encode competing objectives in a fairer and more transparent way. And in our work, by characterizing the priority respecting allocation problem as a weighted matching problem, we're able to find a more efficient procedure to locate good allocations that also gives us the flexibility to consider many different problem extensions. I want to thank you for listening, and I invite you to check out our paper if you'd like to learn more.